So in 7.3 and 7.5, the combined lesson, we're going to be looking at regression functions again. So this modeling right here, that's building regression functions. So you have your data in the calculator, and you're asking the calculator to come up with an equation. So modeling those functions, we're going to be using exponential functions. And of course, in 7.4, which we've already done, we've taken a look at exponential functions that are increasing and ones that are decreasing. Okay, so these have different names when we're talking about, data collection, and we may as well talk about those right now. A decreasing exponential function is called a generally it's modeling some kind of decay. All right, so exponential decay is what this type of function might represent. Exponential decay. Okay, so that's a decreasing exponential function. And an increasing exponential function would be, you'll hear that referred to as exponential. It's spelled today. Exponential growth. Okay, so first part of your notes, you make sure you have that on your notes, that an increasing exponential function is modeling exponential growth. So we're talking about growth of populations, of bacteria in the lab, something like that. Exponential decay, as mass of a decaying animal turns into something else, or the spontaneous degradation of material, or an atom, a radioactive atom or something like that. So that's what we're going to be looking at today, 7.3. We look at the textbook here. Okay, so fruit fly population. All right, so this is something that can be modeled by an exponential growth. Okay, so you see it continues to grow, but not at a steady rate either, right? It grows a little bit, then a little bit more, then a little bit more, and then it kind of starts to build up a little bit. All right. Here's a couple interesting pictures. This is Main Street, Winnipeg in, looks like, what, 1880? Where is it? Yeah, 1880. And this is a picture of the same spot in 2010. So that building there, I'm just guessing, might be sort of what that building was, I guess, in that corner. Okay. So as population grows, a lot of things change, right? So here's your exponential growth function in your textbook, where they kind of describe it. And basically what they're saying is as you move from left to right, the y values increase in an exponential fashion. And it can be modeled by your typical exponential equation. Okay. All right, so we will input some lists into the calculator, and we'll do a couple examples of this. Here's your exponential decay. Okay, so the exponential decay is when we have a b value or a base, right? That is between 0 and 1. So that's how you have a decreasing exponential function, also called an exponential decay. So in this example here, they've plotted points from this data up here. And all these points are plotted, and of course they've modeled this with an exponential equation, and here's the line that's drawn there. Okay, so that's what we'll be doing. That's what we'll be doing today. Any questions so far? You can say I'll save the examples for a little bit. I do want to kind of just go over the main points of this lesson, and then also 7.5. Okay, so any questions on what I just talked about, exponential growth, exponential decay? Okay, that's pretty straightforward stuff. So, all right, so let's move over to 7.5, because 7.5 is also modeling data, but using logarithmic functions. So I'll spend just a little bit more time on this one. We just we're learning about log functions, right? If we go back to the notes from last day, okay, so we're talking about an exponential function, which may be a function like this, y equals e to the power of x, and y equals the natural logarithm of x. So if you weren't here yesterday or forgot about all this, you might need to watch this video again on logarithmic functions, but they are inverses of one another. On the calculator, you see that the log and 10 to the power of x are inverses. Natural logarithm here and e to the power of x are inverses, so they're related. Okay, so in 7.5, okay, oops, okay, in 7.5 we are modeling data using a log function, and on your calculator, when you ask the calculator to generate a line of best fit using the logarithmic function, which maybe I should just go over that again. So a log function sort of looks like this, right? It sort of comes up from negative infinity there and sort of comes up through x equals 1 and kind of just does this. Really, it's the opposite, right? It's the opposite of, or an inverse of exponential growth. So yesterday we talked about this. Y equals x is the reflection line. Here's the log of x. Also, this could also be the natural logarithm. Y equals the natural logarithm of x. So that's what we'll be focusing on today. On your calculator, if you go into the stat menu over to calculate, and then if you go all the way down, what you'll see is here's exponential regression. Okay, so that's what we're going to be using for the 7.3 questions. Exponential, so sort of growth, decay, exponential. It's exp reg, that's 0. And then if we, up here, ln reg. The calculator will give you a natural logarithm expression for regression, not an log, but an ln. So 9 is the function we're going to use if the data seems to kind of fit this sort of thing. All right? So we're going to be able to look at the data, plot them on the calculator like we've always done. You'll be able to see sort of what the general pattern is, and then you'll be able to choose, which one of these would be appropriate. Okay, so let me just erase this and this. Okay, so you're looking at this kind of stuff right here, something that's decreasing, something that's increasing like this, or something that is sort of coming to a maximum point up here, approaching some kind of maximum. Right? Yeah, this growth right here, and maybe I'll just point this out. I'm just going to erase some of this stuff now. This growth right here is a bit different than this growth, right? If you look at this stage and this stage, they look kind of the same. They're both increasing, right? But what you'll notice is that the growth is sort of starting to slow down over time. The rate of growth is slowing down over time, and this rate of growth is picking up over time. And because if you extend this, over more and more time, this keeps growing really sort of out of control. This one here starts to sort of slow down, and like I said before, approach some kind of maximum. So this would be an example like if you have fish in a pond or something, and you have a certain size of pond, there would be some sort of carrying capacity. So fish can multiply and grow, and the population can grow. But because of the size of the pond or other factors, that there would be some sort of limit that they would be approaching. And that would be this sort of function, right? Yeah, and this one, in real life purposes, you wouldn't really have anything that kind of increases and grows out of control to infinity. There would be some sort of limit. However, the limit may not be within the reasonable domain, so you might not be able to recognize a limit, and then exponential growth over a certain domain, over a certain time period, may be better to model that. So these are, I just want to point out, those are similar, but they're not the same. All right, so there may be some choices there. All right. All right, so in 7.5, let's see what else is there. Okay. So if you look at this little example here, or actually let's look at this one because it's got a graph here as well. We won't get into the context, but this obviously is some kind of logarithmic function, right? How it kind of grows, but then it sort of kind of trails off, levels out a bit. All right. This one here, this is tuition fees. for, let's see, post-secondary education in Alberta. So there's a lot of growth there, and then it sort of like levels off. There's nothing gathered there, and then up here. So you could kind of model this by a log, or I don't know, exponential might be okay, but doesn't look like it. So some kind of log function might be more appropriate like this, right? So, yeah. All right, so here is our, now I don't know if the calculator is going to spit this out, we'll check, but y equals a plus b ln x is the format there, okay? So your logarithmic functions, you'll see this in your textbook, a plus b ln x. And what I want to ask you, what do you think a represents? I don't know if it says there or not, but what do you think a might represent? It's some constant there, right? So what would a represent? Go ahead and look through your textbook here, see if you can find what a would represent in these equations. Okay? So if we look at this function in the pattern here, a plus b ln x, if a is 0, so we have virtually no constant there, it's just y equals ln x. This is your y equals ln x. Okay? What happens if we move this a value? What do you think is going to happen? Okay, it's going to stretch maybe. Okay, so stretch which way? Up. Okay. Now I think we talked about a stretch the other day, didn't we? Okay, so which parameter was it that stretched? Yeah, the y value did stretch, but which one of these did we talk about the other day? We talked about b the other day, right? Let's take a look at b. What happens with b? I think there's your stretch that you're talking about. So if you remember from last lesson, if we multiply the y values by a certain value, it stretches them. So this actually, the b is actually the stretch, right? So there's getting stretched up really high, and here is getting squished down 0.3, right? So that's the vertical stretch b. So what happens to a? Well, let's just see. Okay, what's happening there? A little tough to tell. Is that a stretch? Is it the same as the b? So is this doing the same to the function that b is doing? Okay, let's see b again. So here's b. What's the difference between a and b when I'm moving a and b around? What are you noticing? Very good. The intercept, the x-intercept does not change when I move b. So here I'm moving b, and we have the intercept not changing at all. Okay? So what about a? That definitely changes, doesn't it? Now it kind of looks, it's a little bit misleading, I think. I'm going to move this. I'm just going to move this graph over here a bit. It's a bit misleading when I'm moving a around here as to actually what's happening. Okay, but maybe with a bigger picture you can kind of see what's happening. What is happening to this graph? Is it stretching? Is it contorting at all? Or is something else happening? Because with a little view, it looks like it's sort of being stretched a little bit. But with the bigger view, do you kind of see that the whole graph is actually just being moved up and down? I don't know if you can see that. The graph shape itself is not changing. The whole graph is moving up and down. But if you look right around here, right around the axis, it looks like it's shifting. So let me zoom in again. Okay, as I move A there, it looks like it's kind of like bending, it's straightening or something. You know what I mean? It's like it's falling over, right? That's what it looks like. But if you zoom out, let's zoom back out here. A lot. Then look at what, I'm going to play this here. Look at what's happening. See? The whole thing is just moving up and down. See that? So the A value here is simply what is called a vertical translation. So I don't think we've talked about translations much in Foundations of Math 30. In Pre-Calculus 30, we talk a lot about translations, stretches and stuff. Did we do that with you guys or not? I can't remember. We talk a little bit about it, stretches and stuff, right? So this is a vertical translation. It's the whole graph is moving up and down vertically. Okay? So any ideas on how that might be applicable in the word problems? Anyone find anything interesting about that in the word problems there? Now, you don't have to answer that right now. You might come across that. The reason why A is important in modeling data, that may come as you kind of do the questions. Okay? So if we go back to the textbook, so I just want to show you sort of what was happening there. If we go back to the textbook, 7.5, right, let's take a peek at the summary here, okay? So a log function may be a good model for a set of data if the points on a scatter plot form an increasing or decreasing curve where the domain is restricted to the set of positive real numbers. So that's another thing. Go back to the Desmos there. Notice that the domain, the x values, are only positive for a log function, right? Even if we move a around, it's only ever positive. It never goes back to the left of 0, right? So that's a thing. The general form of the log regression model, okay, again, we'll find out if that's exactly what our calculator does or not. It may have, you know, the constant at the other end here, but we'll see. Okay, a log curve of best fit can be used to predict values that are not recorded or plotted. So that's just the same as we've used curves of best fit before. Okay, so let's do an example. We'll plot an example into our calculator, maybe one from each, and we'll go from there. Okay, so let's take a look at this example here. There's not a whole lot of data points for us to put in. There's time and temperature. Let's just read the problem before we start putting anything in. Emma did the same experiment, as before. I guess they were time and temperature. Performed one trial. So at intervals of time, she took the temperature of something. Okay, we don't need to know what the other question was about. But we want to create a scatter plot. So which is going to be the x and which is going to be the y? Which is which and y? W-H-Y. Which one's going to be the x? Which one? Time or temperature? Time? Okay. Yeah, time is right. Now you know why time is right? Why is time x? Why is time the independent variable? Because we start with time intervals, we predetermine time intervals, and then we measure the temperature at those time intervals. So the one that we kind of start off with is the independent variable, that's always x. Okay? The temperature is the responding or dependent variable, so it depends on the time. We start with the time and then we take the measurement. So just take a half a minute here to put those in. So once we have those lists into our calculator, then we are going to want to construct a scatter plot. Okay? So why don't you take on your own there, take 30 seconds and construct that scatter plot. Once these points are scattered, you see that there's a little bit of curvature there. Okay, so it looks like the data points kind of form this kind of thing right there, not really linear. So that's going to be what? Exponential? Not logarithmic, right? It's going to be exponential. So, okay, we'll get to this in a second. Determine the equation of the exponential regression. That models for data. All right, so go ahead and do that. Do you remember how to do that? We'll see if you remember how to do that. Go ahead and try it on your own. And like I say, I'll show it to you again afterwards if you're stuck. Okay, so again, hopefully at this point, you're able to generate that with your calculator. If not, let's just go over those steps real quickly again here. So stat, calculate, you're going to want to go find the exponential regression right there. Right? Hit enter, and then your list 1, if that's where your x data is. List 2, if that's where your y data is. Separate them by commas. And then if you want the calculator to put this stuff right into the y equals, then you hit vars over to function, enter, and then enter again, okay, which I've already done. And you'll get this on your screen, and it will automatically populate your y equals there, right? So the calculator does, in fact, use the same, looks like it uses the same as the textbook there, ab to the power of x, so we're good there. So your equation would be y equals 8.9726 times, and you put a bracket there, 0.972586 to the power of x. That's the equations you would write down on a test or something in your assignment. You would write down that equation. And there it is on your calculator. So graph that. There it is. Now with this, obviously with this, you could calculate points that would be in between your data points, just like we've done in other cases. And again, computer issues here. Not sure where my problem goes there, but here it is. Okay. Okay. At what time to the nearest minute did the water reach 51 degrees Celsius? So let's try and answer that question. At what time to the nearest minute? So time is x value, right? And temperature is the y value. So if we're given that we want to find the time for 51, anybody remember how we want to do that? 51's on here. What do I have to do? Let's go ahead and shout it out. What do I have to do? Right on. Yes. Y equals 51. Put that in as another function. And then graph that. Now there's a point that's pretty close there, right? Looks like there's 52. So that's going to run right by that point that's already in there. But we don't have the 51, so let's use the calculator to generate that. And then we can just generate the intersection point, right? So second function calculate 5. First curve, yes. Second curve, yes. Guess, yes, please. And your cursor should show up right there. And so at 51 degrees, that's exactly 20.323965 minutes. Okay? So on your assignment or on your test, it won't be good enough for you to say about 20 or 19. I want the exact number because I want to see that you've been able to do this on your graphing calculator. Okay. Any questions on that? Okay. I think just to conclude, we'll do one more example using a log regression. So if you want to clear your list really quickly, hit second function here, and then see the memory. Second function plus sign, which is the memory, and you get to number 4 there, clear all lists, and then hit enter. Don't delete the lists. That's what some people have done. Don't delete lists, but then if you go to stat there, then everything should be cleared off. Okay. So that's a quick way to clear all the lists off. You just want to kind of start from scratch. All right, so let's take a moment to put our data in here. Again, if we read the question, we'll be able to tell what is our x and what is our y value. So the flash on most digital cameras require a charged capacitor in order to operate. The percent charge Q remaining on a capacitor was recorded at different times t after the flash had gone off. Okay, so what are we starting with? What's the independent variable? Is it the percent of charge or is it the time? So are they recording the time when they've reached a specific percent of charge? And that's what they're writing down, they're measuring the time, or are they taking the time and at a certain time they're measuring the charge? Yeah, it's the second one. So this is the variable we start with, so that's going to be our t. Okay? So, and you can also kind of tell that this is all rounded to, thank you, it's all rounded to kind of a, the same, hundredth there, so, this is not obviously something they started with. This is what they started with, this is what they measured. So take a moment to populate your list there, this being Okay, so when you graph this, adjust your window, and you should be able to see this. Okay, now that looks to me like it could be an exponential function as well. But you'll find in the textbook that they used a logarithmic function. Okay, so why would a log function be more appropriate here than an exponential function, do you think? So what I'm saying, right, is that kind of looks like a piece of, it kind of looks like a piece of an exponential function, but they are going to be using, we're going to use here, a logarithmic function that would look more like this. So why would this second one be more appropriate in this kind of real life example? What's the main differences between these two graphs? Okay, this one doesn't cross the y-axis. Okay, yeah, which means that there's no negative values for x. So does it make sense in this situation that there's no negative values for x? Like there isn't. And what is x actually? It's time, right? So you can't start collecting data before you start collecting data, right? You can't say, here's the measurement 0.1 seconds before I started. Doesn't make sense. So yeah, that's exactly right. Very good. So the negatives don't make sense. So maybe a y equals some kind of ln function, right, would be better. Okay. All right. So let's go back there. So let's get the calculator to do that. So stat, calculate. Okay, we're going to go up to which one? Ln reg. Okay, natural logarithm, abbreviated ln. So let's tell it our lists. List 1 for me, list 2, and then I may as well get it to put that right into the y equals as well. So just like stuff you've done, a dozen times here now. So let's see if that's going to work. Oh, I hit graph, not enter. Sorry. Enter. Oh, 2. Domain range. Okay, what's wrong with the domain range here? Ln reg, list 1, list 2. Okay, I've got some problem. Did you guys get yours to graph or no? Did it come up with the same error? Oh, okay, well let's figure that out here. I was expecting that. So domain 0. Oh, I see. What's the problem here with my domain? What's the problem? Now we have to go back to that question I asked you before about the exponential and ln. Something's wrong. What is the problem here? Right, for a ln function, natural logarithm or logarithm function, you can't have, like, x will not equal 0, right? So if we go back to here, this will approach 0, but it won't actually it won't cross it, you're right, but it won't even touch it. So if we have this point in there, we've got a bit of an issue. Okay, so what we have to do is we have to figure something out. If I want to use a ln function, which is great, I think that's a good thing to do, but what do I have to consider here with my data? Yes? Did you find something or no? No. Anybody else? Okay. So here's the thing. If you come up with that error, all right, and you've done everything you're supposed to, you've put the points in there, but you say, okay, a natural logarithm or a logarithm equation cannot have a 0, x equals 0 point. Okay? So my question is, I guess the question would be then, does this 100% charge at 0 seconds, how important is that to the data? Do we know this? Do we know this already, that we're going to have 100, that's where we start? So is it important to have in our data table? Not really. It's not really important. So if you go back to your data, this is not really that important in this case. So let's clear that. Okay. Maybe I have to just delete it. And let's go over here and delete that, 0 to 100. That's not really important. So let's go back to calculate, exponential, nope, logarithm. And okay, I'm going to have to clear this. Okay, so stat calc up to 1, that's number 9. List 1, comma, list 2, comma, vars, over to function, enter that, hit enter. Okay, so it gives us this, and if we graph it, we get something that looks like that. Now, to me, that doesn't look like a great line of best fit there, does it? Okay. So what we're going to have to do is we're going to have to figure out if we're going to use a different function or what. So before you go, your job is to, before next class, sometime I want you to remember what calculator you have, and I want you to try and get a better line of best fit, whether it's exponential functions, your only homework for tonight, okay? But you need to work on this. I need you to get a better line of best fit. So do we have to change this point again? Do you have to use something different? So that's your challenge for next class. All right, I'm assuming you've had a chance to play around with the numbers here. What I'm showing you on the screen is this right here. This is our original natural logarithmic function that we said didn't really look very good. I did try an exponential function that seemed to fit really, really well. So for our calculator, the best line of fit is going to be this exponential function right here. So it looks like, and I'll show you what's going on with the other one. So here's our original function. As far as a logarithmic function, that's going to be your logarithm of best fit. Okay? So what you're going to want to do is, in order to get that logarithm to actually set up, you're going to have to go into stat, you're going to have to go into enter, and then just notice what I did here. I took out that 0, 100, and what you're going to want to do is replace this with something that's not 0 but very, very close. So I just put in point 0.00001, and then it's not 0, and the calculator will give you that, that function. So as far as the natural logarithm, that's going to be your best line of best fit. The exponential function seems to be better, but for our technology, that's the best logarithm. These ones are, that's not a good fit, but that comes when that 0 value is 0.00001. That's what you get.